to go over the lab stuff tomorrow and make sure that you understand the calculations on the lab stuff. If you miss the lab, if you were not here the day of the lab, I have these packets up front. Oh, sorry. So if you were not here the day of the lab, you'll need to grab one of these packets. In Gizmo, so go into Clever, go into Gizmo. There should be a Gizmo assigned that is called Calorimetry Lab. This is only for people that miss it. This is going to replace your lab grade. All right. So you'll need to do that. You'll need to do the quiz that's associated with all that. I'll post an assignment for it, but I have to go through and actually physically look who was absent and who wasn't. So I haven't done that yet. Yes. Yeah. Yeah, I'm going to explain some of the math stuff of it tomorrow. So, just be aware that that's coming. All right. All right. So today we're beginning chapter 5. Chapter 5 is bonding. So our goals for today is to identify the 4 primary types of bonds. We're going to define a chemical bond. We're going to explain why chemical bonding occurs at the most basis level. And then we're going to distinguish between types of bonds. Our focus today, we're mainly going to focus on one type of bond, which is an ionic bond. All right. So that's going to be kind of our goal today, is writing chemical formulas and naming ionic bonds. All right. But I'm going to go through some background stuff first and we'll jump right in it. All right. So if it helps you to think of atoms this way, you can kind of think of atoms like Lego bricks or jigsaw puzzle pieces. They fit together in certain ways, and they're going to form patterns. All right. So just like we know that water is always H2O. All right. And that's because of the way an oxygen and a hydrogen have with their electrons, and that's because of the way they share their electrons and things like that. All right. So when we're dealing with bonding, the number ratios happen in a certain way. So if you look at this one, that first one, you have Al plus 3, and O negative 2, O negative 2, O negative 2. So what that's actually telling me is that I have 2 aluminums and 3 oxygens. That one tells me that I have 2 sodiums and 1 sulfur. This one I have 3 calciums, 2 phosphoruses, and so on. All right. So all of those form certain patterns. They're only going to fit a certain way. So that's what we're trying to accomplish today. All right. Here are the 4 types of bonds. And it's going to feel like I'm trying to rush through this today, because I am, because it's not a lot of mental stuff. It's more just words. All right. Today will be the only time that you hear me talk about a metallic bond. A metallic bond is when we just have a hunk of metal like copper or tin or something like that, and it's only atoms of that metal. Metallic bonds are physically attracted bonds. So one atom of copper is physically attracted to another atom of copper. They can exist in the same space, and they're just right next to each other. And their electrons can actually flow from one to the other because they're electrically conductive. All right. No special kind of bonds really apply to metallic bonds. the second type, ionic bond, what word do you see in ionic bond that kind of clues us into what type of atoms are involved? Ion. So ionic bond's going to involve charges. And in order for two atoms to stick together, what kind of charges would they have to have? Like charges do what? Repel. Opposite charges attract. So an ionic bond is going to involve oppositely charged ions. All right. Covalent. What's some other words that use that prefix co in it that you can think of? Think about maybe like relationships. Cooperation, co is there. Codependence. There's things that need each other to function, right? So covalence means that they're going to share their outer shell electrons. All right, so they are covalent. All right, in covalent, there's two types of covalence that we will look at, and we're going to focus on covalent tomorrow, but polar covalent and nonpolar covalent. Polar means it has, the ends of it sort of have a charge. All right. Nonpolar means that it's all going to have the same charge throughout, or neutral, something like that. And then acids are a special type of covalent that involve compounds with hydrogen in it. All right. We're going to talk about all four of these types by the end of this week. All right. So what is a bond and why do they form? A chemical bond is simply a force that chemically holds one atom to another in a compound. All right. So that's going to happen in two ways. Either electrons will be transferred, which means that it's going to be ionic because we're going to form a cation, which is positive, and we'll form an anion, which is negative. So if I give an electron from this one, it makes it positive, and this one's going to take it and make it negative, and then they're attracted together. And then the other way that a chemical bond happens is by sharing electrons, which is covalent. That's when your electrons stay in your valence shell, but you remember everybody's goal is to get to 8, and the way that they get to 8 is by borrowing the electrons from somebody for a little bit, and then they give them back so that the other one has 8. So they kind of just do this equal exchange of electrons. Yes. Yeah. All right. So now we know what a bond is, but why do they occur? So if you have to leave for work first Wednesday, you can go ahead. If you're one of those people with the passes and all of that. All right. So The whole goal of bonding, the reason why bonds form, and this is pretty much the whole driving force of why we study compounds in chemistry, is the whole thing is we're trying to watch how energy exchanges. So bonding occurs to get to the lowest energy state. Now, this is only for visualization. This is not a real way that it happens. All right. But if I have a sodium atom and I have a chlorine atom, and they're both sitting on top of a hill. All right. Think about this in terms of kinetic and potential energy. They have more energy right here by themselves because they're higher, right? All right. So as these atoms start rolling down the hill, they gain some kinetic energy. So let's just say that the sodium gets an electron knocked off of it, and chlorine picks up an extra electron as it happens. So as they're going from here to here, they've lost a little bit of potential energy, but gained some motion. All right, maybe gain some heat. And then they get down here where they combine together, and then this is their lowest energy position. So they're happier, or they're more stable because they're in a low energy position when they're in a compound. They're less stable when they're by themselves because they're in a high energy position. All right. So breaking a bond requires energy to overcome the force of attraction. So I have to add energy to a compound to make it break. Bond breaking is endothermic. Means it takes heat in. All right. Bond making, or creating bonds, releases energy, so it makes it exothermic. All right, now, so couple of examples, real world, that you've probably seen. When you were kids, at some point, whether it been at school or at home, just because you were curious or whatever, you might have mixed vinegar and baking soda just to make the bubbles, like to do the classic volcano thing, whatever. All right. If you touch the side of the container when you mix baking soda and vinegar, you should feel it get cooler, or it should feel like it's getting cooler. And that's because you're breaking bonds there in that sodium bicarbonate. You're releasing some of these bonds, and so it's endothermic, so it feels like it's cooler. All right, because it's taking energy from outside to make that reaction happen. All right. However, if you've ever had the little hand warmers, you went camping or you went to a parade and it was cold and you got the little hot hand things that you put in your pocket, that's basically just a packet of metal that has pores in it that it can have air flow through it. When metals interact with oxygen, they oxidize. They rust. That process of rusting is an exothermic process, so it feels like it warms up in there. So as that's happening, you're giving off heat. You're making bonds. So you're going from just a hunk of iron to iron oxide. And so you're generating heat off of that. All right, any questions on that? All right, now, so let's start looking at a chemical formula. So there's three parts of a chemical formula that I'm going to talk about today. And so whenever I'm talking about the chemical formula itself, I'm really just, I'm talking about all of it there, all the numbers involved, but mainly just the symbols and the subscripts. So go ahead, copy down this chemical formula, 3Na2O. All right. And so this part that I have circled, this is the chemical formula, or the molecule. All right. Now, we're going to learn by the end of class today that this is actually an ionic compound because sodium's a metal and oxygen's a nonmetal. But, so instead of a molecule, when it's ionic, we call it a formula unit. All right, ionic compounds are going to be called formula units. Covalent compounds are technically called molecules. All right, and I got a little out of order on my things because I made the wrong thing show up. All right, so I'm going to deal with subscript first. This number 2 right here represents a subscript. What does that subscript identify in that compound? What does it tell me? All right, so, well, first off, which symbol is it relating to? Is it relating to the sodium or the oxygen? Sodium. All right, it's always going to be the one that it's following. All right, so that tells me that I have 2 sodiums in this compound. All right, now it tells me it's 2 sodiums for every 1 oxygen in that relationship. So anytime I have sodium oxide, it's going to be Na2O. That's the formula for it all the time. Now, the other thing is the coefficient. And in math, when you hear the word coefficient, where does a coefficient appear in an equation? Usually next to a letter or in front of a whole system, right? Outside the parentheses, in front of a whole system. Well, in this one, coefficient does the same thing and it appears the same way. Coefficients are always going to be large, full-size numbers. Subscripts will always be in a lower position and smaller. All right, but that coefficient in math, what does a coefficient do to the number it's next to or to the variable it's next to? It's a multiplier. That coefficient is a multiplier as well. So if I wanted to look at this in terms of what's going on inside the system, what does that 3 in front of there now tell me about sodium? There's 6 sodiums. What does it tell me about oxygen? 3. What does it tell me about total number of formula units? Well, this total number of atoms is 9, but total number of formula units is I have 3. All right. Formula unit. When I say formula unit, I'm talking about the Na2O, the whole thing. All right. So the next slide is just going to rehash what we just did with the numbers. So, all right. So looking at this chemical formula again, a little more specifically. That 3, that coefficient is a multiplier. It's going to multiply to everything in there. So in terms of, I forgot my coefficient, my subscript. In terms of the molecule or the formula unit, I have 3 units of Na2O. So when you start looking at the active questions, when you start looking at the questions on a test, the way that they might say this, they might say that you have 3 mole of sodium oxide. All right. That 3 represents a mole or represents units, but we have 3 total packages of sodium oxide. All right. And again, if it was asking a question about how many sodium atoms there, we have 3 times 2, so it is 6 moles of sodium atoms. And then we have 3 All right. So one of the things that is going to hang you up as students is just terminology that they use. Saying 6 sodium atoms and 6 mole of sodium atoms is really saying the same thing. It's just kind of a way that we can express it, clarifying some things. Now, Mike brought this up earlier, that we have 9 atoms in total, right? Because I have 6 sodiums and I have 3 oxygens, so I have 9 atoms in total. So another way that you might see this written is 9 mole of atom in the compound. 9 mole of atoms in the compound. All right. You're not, that term mole, I'm going to further define it a little bit later, but I just want you to be aware of phrasing. All right. So now we're going to look at an individual chemical formula, and we're just going to try to find out some information about it. So we're going to see what we know at this point. All right. Anybody still copying, need more time? All right. So how many moles of CaOH2 do I have based off of the top formula there? How many units of CaOH2 do I have? 2. All right, so does everybody understand why I'm saying I have 2 units of it? All right, how many moles of calcium atoms do we have? 2. All right, how many moles of oxygen atoms? 4. Why 4? All right, so that parentheses is telling me that I have 2 oxygens and 2 hydrogens in there, and then the coefficient is telling me that I have 2 groups of that. So yes, I have 4 moles of oxygen atoms in this. And then what about hydrogen? 4. Now, before I go any further, the reason why I wrote this inside of parentheses is because this represents a polyatomic ion. So some compounds are going to have this group of 2 atoms that forms a ion that we have to keep these together. So the reason why I use the parentheses is because I wanted to represent that I have 2 groups of OH. So the ion that I formed here is an OH negative, which is called a hydroxide. So how many moles of hydroxide ions do I have? And I actually have something wrong on the... All right, so I have 2 times 2, right? So, and I think nope, I have the wrong number there. That should be 4. So I have 4 hydroxide ions. So I have 4 groups of OH because I have 2 times 2. All right. So just like now, before I move off of this, do you think that if I was asked to write this on the test, if I was asked to write a formula between combining calcium and hydroxide, and I wrote it like this, do you think I would get credit for that answer? Okay. Why wouldn't that why do you think this and this are not the same thing? Well, I do have the 2. I just moved it. So it's the same amount of stuff, but saying it like this represents a whole different type of bonding than this. So this would be incorrect. I'm not going to distribute any numbers in there. This CaOH2 is a defined pattern. It's a defined ratio. For every 1 calcium, there's 2 hydroxides. So whenever I deal with that, that's why. Yes. 2 times 2. Got it? All right. So we're just multiplying everything in there. All right. But I can't change the way the formula is written. I have to write the formula a certain way. So that's kind of where we're going. That's where we're going from this point, is how do I know what the formula should look like? So our goal for today is we want to be able to write and that's a very bad and symbol, but we want to be able to write and name ionic formulas and compounds. So I want to be able to write the name of it, and I want to be able to write the formula of it. And I want to be able to go backwards and forwards with these. All right, so first thing that we need to know is, how do we recognize an ionic compound? Ionic compounds will typically contain a metal and a non-metal. So from the previous chapter, we should be able to recognize, looking at the periodic table, if I write something down, which is the metal, which is the non-metal. Right? If it comes from the left side of the periodic table, it's a metal. If it comes from the right side of the periodic table, it's a non-metal. Another way to look at this is, what type of ions do metals typically form? This is from chapter 3 as well. They form positive or negative? Metals, positive. Things on the left side form all right. So metals tend to form positive ions. And just for funsies, what do we call that positive ion the way it's spelled? It's a cation, not a cation. All right. All right. And then nonmetals tend to form negatives. anion, not an anion. All right, now, so I like to use the phrasing that an ionic compound is going to contain a positive ion and a negative ion, or a cation and an anion, simply because when we start throwing polyatomic ions into the mix, students get confused that they say, well, where's the nonmetal, or something like that. All right. Now, if I look at if I look at a compound made of strontium and sulfur, which one of those is the metal? Which one is on the right side of left side of the periodic table? All right, so that is my metal. That is my all right. Now, so whenever I look at this, I should be able to recognize an ionic compound just simply by the presence of a metal. There are a couple that kind of defy the rule, and as we get deeper in this, I'll bring those up. All right, so that metal non-metal is kind of a general rule, but it can't be broken. All right, so just kind of know that. So ionic compounds, we use the oxidation numbers. Last chapter, chapter 4, and I guess chapter 3 too, when I was talking about the periodic table and atoms, I didn't necessarily call them oxidation numbers. I called these ionic charge. They're the same thing. So if you think about your periodic table, I have group 1A, group 2A, group 3A, group 5A, 6A, all right. These are our main group elements, right? Alkali, alkaline, boron family, nitrogen family, oxygen family, and halogens. All right. What charge does group 1A typically have? Positive 1. What charge does group 2A typically have? What charge does group 3A typically have? Plus 3. All right. Now, going over here on this side, what charge do we normally associate with group 5A, or the nitrogen family? It's going to be a negative 3. All right. What charge do we typically associate with group 5A, oxygen? Negative 2. And then group 7A is a negative 1. All right. Typically, carbon family doesn't really form ions unless you're talking about SN and PB, and they're going to be treated like a transition metal if they have more than one charge. So I use just these when I'm talking about charge, when I'm talking about oxidation numbers that are known. All right. These are kind of like permanently assigned this or this. All right. So now, when we're dealing with ionic compounds, you're always going to have a cation and an anion involved. And they're going to match together in a way that the compound is neutral, has zero net charge. So there's going to be two different methods that we can do this. So let's just pick some random elements here. All right. I want to form a compound between rubidium and phosphorus. All right. So I'm going to show both of these methods kind of the same way. Neutralizing the oxidation charge and crisscross method. I'm going to show crisscross method first because it's the simplest. All right. So looking at these two elements, what charge, based off your periodic table and location on the periodic table, what oxidation number or ionic charge should I assign to rubidium, Rb? A positive 1. What charge should I assign to phosphorus based off this location? All right. Now, my overall charge of the compound, compounds are always neutral. So my overall charge has to be 0. So I need to establish a ratio of these charges to get there. This method is going to work 99% of the time. That all we really have to do is take the number, not the charge, just the number value, and bring it down there, and bring the number value down there. All right. I don't have to show the one. The one's going to be kind of understood by the fact that I have the symbol. But if I want to write the formula for this, now, how do I know that this works? All right. So the method that I just showed you is the crisscross method. How do I know that this works? Is because I can algebraically look at this. If I know that my compound has to equal 0, yes. If I know that my compound has to equal 0, and I have three positive ones plus 1 negative 3, what is 3 times positive 1 plus negative 3? All right, equals 0. All right, so when we look at this, and so what I did here is I essentially neutralized the oxidation charge. All right, so this is the way that I would get to the other one. Is I'm going to set the equation to 0, and I have to figure out how many of each I need to get to 0. All right. Before does everybody have the little example I have written down? All right, because I erased it and I want to bring something else up now. The only caveat to this, and the reason why I said crisscross works 90% of the time, is every once in a while we'll have a situation that gives us a formula when we use crisscross that is not in the lowest whole number ratio. So the formulas always have to be written in lowest whole number ratio. So an example of when crisscross doesn't totally work. Let me do. And so for this one, I have to, I'm going to have to show it like this. So some compounds, you'll see something written like this. All right, so I have this lead with a Roman numeral 4 following it, and then oxide. So lead 4 oxide. And the teacher, the program, the professor says, what is the chemical formula for lead 4 oxide? Well, now we have to start using context clues to figure it out. All right, so we don't know. This should look kind of weird to you, and this looks like something that you may not have seen yet. All right, now what can we get about this one from context clues? What element is this representing? Oxygen. All right, what do we know about the charge of oxygen? It is a negative, and it should be a -2 because of location. All right, now notice where lead falls, and notice that I didn't really give you a charge for that column, right? So I don't necessarily know the charge of this one. That's because that lead and tin and the ones right next to it, SB and BI, so SN, PB, SB, and BI, all of those can have more than one charge. So when you see something written like this, this is actually telling you the charge of it. So lead is the symbol PB. What charge is it telling me that it is? If I see that Roman numeral 4, that tells me it's a +4. If I saw a Roman numeral 2, it'd tell me it's a +2. Yes, ma'am. Yes, ma'am. All right. Now, using crisscross method, what would be the formula that I would get for this? So I'd get PB2O4. Is that written in the lowest whole number ratio? No. So how do I fix this? So that's going to be my actual compound because I divided each of those by 2. Now, so the reason why I know this is my final formula, because if I look at it algebraically, if I look at it mathematically, and I'll write it up here. All right, so if I look at it like that, now, if I'm looking at it algebraically, I know that oxygen's a -2 and I have 2 of them. So I have 2 times -2. And then I want to know what my PB is because I don't know the charge of that lead. I can solve for X there. So if I solve for X, that means that X has to be a +4 in that case. Because 2 times -2 is -4. Bring it over to the other side. X equals +4. All right. Questions? All right. So I want you to try to come up with the formula for a compound formed between calcium and chlorine. So using what we just did, I want you to do this on your own. Yes. Oh, your flower babies.
That's for me, Elena.
Is it a girl or a boy? What are their genders?
It doesn't have a gender.
Yours isn't a flower baby, it's a rice baby.
Yeah, mine's rice. That's just what I had in my pantry.
Why did you drop it, bro?
Then I have to fill out an accident report. Hi, this or not. And have to write an essay.
All right. So now Ca is a +2, it's a positive ion. Chlorine doesn't form -3, chlorine forms a -1. So, all right. All right. So let's look at this real quick because I want to try to get to a certain point today. So, guys. All right. What do you think the formula should be? All right. Trying to get to CaCl2. Now, check why we got there. All right. So, looking at it in terms of oxidation numbers, when I look up calcium, calcium has a +2 charge. When I look up chlorine, chlorine has a -1 charge. So when I'm looking at just charges, if I have a +2 and a -1, it's going to take two -1s to equal or to cancel a +2, because +2 and -2 are going to cancel each other out. Crisscross method, bring the 2 here, I bring the 1 here, and so I get CaCl2. And that little dot shouldn't be there. That was just I set my pen down on the screen. All right. Now, in terms of electrons, what happened? All right. Calcium forms a positive ion by getting rid of its electrons in the outer shell. So calcium loses its 2 electrons and forms a +2 ion. Each chlorine gains 1 electron, form a -1 ion. So chlorine gets to 8 electrons in its outer shell because it takes one each from calcium. Calcium gets to 8 in its outer shell because it loses the 2. All right. So either way, we end up with that CaCl2. That's just 3 different methods of getting there. Don't feel like you have to do all of them. Most of the time, this works. And then you just have to remember to reduce if you didn't. All right. So questions about that? All right. Try these real quick. See what you come up with for formulas. All right. Just to maintain timing. All right. check your answers and ask questions. All right, any questions? All right, the only one that might have been any extra step is number 3, because if you just do crisscross, you're going to get TI 204, and then you have to reduce it. All right, now, next thing I want to introduce is this polyatomic ions. When polyatomic ions are involved, parentheses may be needed. Don't worry about writing the rest of that. All right, we're going to talk about why and how and what makes them important. All right, so first thing we need to be able to recognize is what is a polyatomic ion. So you need your periodic table reference packet, and I want you to turn to the 3rd page. All right, so this is a list. If you look on the 3rd page of your periodic table reference packet, this is a list. It's on the left-hand side. It's a list of the common polyatomic ions. So you should have this exact thing. All right. Somebody find chlorate. What is the formula for a chlorate ion? Chlorate. All right. ClO3. And then because it's an ion, it's telling me I have to associate a charge with it. So this -1 charge is for this entire formula. All right. We're going to treat this as if it was a singular atom when we do compounds with it. All right. Now, find chlorite on there, and what change do you notice in the formula? So chlorite, notice the charge doesn't change, but what does change? The oxygens, the number of oxygens. The subscript does change, but it's actually telling me that the number of oxygens changes. All right. Now, find this one. Find perchlorate on there, and what do you notice? And then lastly, find so if I was going to memorize this list, what would be a good place to start?
What's it called? The prefix. Oh, and the something.
I would start with the 8s. I would only memorize the 8s off of this list if I were to memorize anything. Because if it goes from 8 to 8, that means it's just one less oxygen than it is. If it goes to 8, from 8 to per 8, that's one more oxygen. All right. And if it goes from ite to hypoite, that's 2 less oxygens from the ite, or 1 less oxygen than 2 less oxygens from the ate, 1 less oxygen from the ite. All right. So I'm not going to ask you to memorize these. What you'll find is the more that we use them, you're going to get familiar with certain ones. By the end of this course, I'll say nitrate, and you'll know it off the top of your head. You should. All right. Carbonate will be another one that we'll see multiple times. But if you ever get one that's not on this list, but if it has an 8 version on this list, for example, iodate, I think it only lists iodate on there. But you might have a question in active that asks for iodite or per iodate or something like that. You should be able to get there just based off of the context clues. All right. So we're either going to add or subtract oxygens based off of what's there. Notice that there are a couple of them that are positive ions. They're not all anions. And that there are some, like that one that says mercury 1, is just kind of like an anomaly. It's just one element. But everything should have something in an oxygen or at least 2 elements involved in it. All right. So let's look at an example of writing a formula with a polyatomic ion. Which one of these 2 symbols represents the polyatomic ion? The CO3 negative 2. What polyatomic ion is this? Carbonate. Carbonate. All right. Now, and I'm going to tell you that version of iron is iron 2. All right. We don't really need to know that to make the formula because I gave you everything you need to know. But what formula should we get with this? All right. So if I do crisscross, 2's going to go there, 2's going to go there. So when I reduce it, if I do crisscross and I do the unreduced version of it, and I need to show that there's 2 of those, but I'm going to use parentheses to show if I need more than one of it. But when I reduce it, it should just be Fe CO3. So, so my answer is FeCO3. The name of this compound, I'm going to start introducing this because I want to make sure we get there. All right, that one's iron 2 carbonate. But what if I wanted to know the formula So based off of context clues of what I've just told you and just showed you, what if I had iron 3 carbonate? What information does that give us? So carbonate, I should be able to look up, right? That's CO3 with a negative 2 charge. If iron 2 looks like this, what do you think iron 3 looks like? So what compound would we get when we do this one? Fe2, and I'm going to write it just how y'all said it. How do you think that looks correct? No, because that's saying I have 33 oxygens, and I don't have 33 oxygens. So I have to include the parentheses to know that I need 2 groups of CO, or 3 groups of CO3. All right. All right. All right. You probably need to report that. Tossing your baby up in the air. That's just that'll get social services called on you. All right. Go ahead, try these 3, see what you come up with for the compounds. They're not allowed.
I know, it's so stupid.
The reason why,
Because it's not a school color.
well, the reason why is East St. John is colors is black and yellow. So we don't want, and they're Wildcats too. We don't want to be.
That's so stupid.
We're same division, same classification.
We win more games. We can just kick them out.
Right now.
They are black and yellow.
But that's the reason why we don't do black uniforms.
That's dumb.
Because and that's also why we specify fighting Wildcats and not the Wildcats. That's something that's been going on for much longer than y'all have been alive. So
The black uniforms will look good. Be honest.
maybe.
No, they will. What about black tennis uniforms?
Well, the girls get to wear black skirts, so
Wow,
and we wear black shirts.
Yeah, but the boys.
I mean, I guess if they wanted to, they could.
The
But
football team can't have a black uniform. I see where Deshaun's priorities are.
well, the issue with that, you're expecting to get those uniforms dirty. I really don't. Sitting on the bleachers and all that we do while we're waiting for our match, I don't want my guys or girls getting up with a green or brown stain on their skirt or shorts. So I don't use because the bleachers have like grass, and
Oh, I didn't know what you were talking about.
if it's a wooden bleacher, it sometimes has that green funk growing on it and all that. So light colored uniforms for bottoms for tennis is not a good thing. All right. Now, let's go ahead. I have 10 minutes, so I want to try to get this done. All right, so going to naming. We've been writing the formulas. Going to naming, we have to basically just have to undo what we've done. So when we're looking at a formula, so if I have a formula like MgO, a binary compound, 2 elements, I'm going to name the cation. So what is the name of the cation in this compound? All right. So Mg represents magnesium. The second part of it is I name the anion, but I change the ending of it to IDE. So O represents oxygen. I'm going to change the YGEN to IDE, and O becomes oxide. Now, that works great for just regular binary ionic compounds that are main group elements. There's 2 other scenarios that can happen. What happens if a polyatomic ion's involved? So I will use, I'm going to stick with magnesium. But we have this formula now. So I do everything the same. I name magnesium as it is. But when it's a polyatomic ion, I'm not going to change the name of this. So what polyatomic ion is NO3? Look at your sheet. Nitrate. So when it's a polyatomic ion, we have to look, we're going to use whatever name is given in our polyatomic ion list. All right, so MgNO3 becomes magnesium nitrate. So notice if it's binary, the ending is IDE. If it's a polyatomic, you're going to see an ending like ATE or ITE. And then the last scenario is what happens if it's a transition metal or a multivalent charge. So whenever I'm talking about transition metals, I'm talking about this group of things here, these, and SN, SB, PB, and BI. Those are all going to be considered transition metals. All right. Those, we don't know the charge. So if I just give you a compound of SNO2 and I'm asking you to name this, when I look this up, what element is SN representative of? That's one of the special ones that I asked you to memorize. It's 10. All right. Now, I don't know the charge of 10, so I have to figure it out. So I know that the compound is equal to 0, right? I know that oxygen is a -2 charge. So I want to find out the charge of 10. So what is the charge of 10 in this case? 4. So I'm going to say 10(4) oxide. Notice that the thing that I put in parentheses in the name has nothing to do with any subscript on this one. All right. Whenever I name a ionic compound, I'm not concerned with the subscripts. I'm only concerned with, the only time I'm concerned with any number on a polyatomic ion, only time I'm concerned with any number on an ionic compound when I'm writing the name is when it relates to a transition metal, something that has more than one charge. So let's show this real quick. In your periodic table reference packet, on the second page, there should be a table on there somewhere that says selected transition metal ions, and it's going to look similar to this one, but not exact. That one has some of the ones that have multiple charges for it. It kind of helps you see them, but it's not all of them. It's not all inclusive. Just know, since we do not always know the charge of a transition metal, we have to use context clues and other tools to determine the charge in the compound. All right, we're going to represent that in the name with a parentheses. All right, so for tomorrow, just give us a starting place tomorrow. 2, 3, 4, 5, 6, 7, 8. Take one, pass it back, please. 6. Take one, pass it back. I would like for you to do the front of this only for tomorrow. 1, 2. Technically before the end of the quarter, but as soon as you can get it done. Do you want to take one for? All right. Yeah, I'll post it. All right.
Wait till it turns 30. We still 25. No, it doesn't. No, it doesn't.